Hello, and welcome to the video on radiation safety for the Department of Materials Science and Engineering at Johns Hopkins University. The purpose of this video is to acquaint you with some of the risks associated with using radiation-producing equipment, how those risks can be mitigated, and the proper use of radiation-producing equipment. When we think about radiation-producing equipment, we're talking about analytical instruments for analyzing typically the structure of materials. We also sometimes use radiation in the form of radionuclides, radioactive materials, but those are not used very commonly in our department and will not be discussed in this briefing. In terms of analytical instruments, the most common ones are the X-ray diffractometer. We have several of these in our department, and there also are several in physics and in earth and planetary sciences. X-ray fluorescence spectrometers, although there are actually none of these on campus. Their basic principles in terms of how they produce radiation and the risks are similar to X-ray diffractometers. Electron microscopes also produce radiation, although at a much lower level than X-ray diffractometers. X-ray photoelectron spectrometers use X-rays in surface analysis. And finally, Auger electron spectrometers also use radiation. To give you an idea of how X-rays are produced in a typical diffractometer or fluorescence unit, X-rays are produced when electrons at high speed strike a target, typically copper. When that happens, the electrons give up their kinetic energy to the copper. As the electrons give up their kinetic energy, they produce X-rays directly. That's called Bremsstrahlung or braking radiation. Also, the electrons have the ability to ionize the copper atoms. And once the copper atoms are ionized, they can undergo transitions to lower energy levels by producing what are called characteristic X-rays. The X-rays then come out of the X-ray tube, typically through a window, typically made out of beryllium. It's worthwhile pointing out that when we look at this sort of diagram, that there are hazards associated with X-ray equipment besides the production of X-rays themselves. And in particular, accelerating these electrons toward the anode typically occurs over a potential of 40 to 50,000 volts. So X-ray producing equipment also produces high voltages, which is something you need to be aware of. In general, you should never be poking around the inside of an X-ray diffractometer unless, of course, you've been properly trained. Primary hazard, though, that we'll worry about in this briefing are these X-rays. And it's always useful to start out by talking about units for exposure to X-rays, which are perhaps not very familiar to people who have not used radiation in the past. What we worry about is energy absorbed by the body. And of course, we normalize this to a per unit mass basis, and that's called the absorbed dose. The SI unit for that is called a gray. A common unit is called a rad. And the conversion is 100 rads is equal to 1 gray. However, doses are not all created equal. In particular, different kinds of radiation produce different effects or different levels of effects on the body. So the concept of equivalent dose takes into account the damage of different kinds of radiation on tissue. And so the SI unit is now the sievert, and it's simply a gray multiplied by a weighting function, a weighting factor. And the common unit is called the rem, and now 100 rems is equal to 1 sievert. For our purposes, a rem and a rad are equivalent because the weighting factor for X-rays and for electrons is equal to 1. We should point out that for neutrons, the weighting factor can be significantly higher. We do not actually have any neutron sources on campus, but it's worth noting that sometimes our students do go to places like NIST or Los Alamos to use neutron sources there. So it's worth noting that neutrons in general are more dangerous than X-rays in terms of their effects on living tissue. Finally, there's the concept of effective dose, which simply takes into account the fact that the damage depends on where the dose is absorbed in the body. Certain tissues are more susceptible to radiation than others. The biological effects that we're worried about come from, as I said, the energy transfer into living tissue. That energy transfer can disrupt the molecular structure in a way that we'll talk about. And the most damaging interaction is ionization for the following reason. As X-rays are absorbed, they ionize water. Those water ions then interact with other water molecules to produce free radicals and oxidizers. Those radicals and oxidizers can then attack chromosomes, and the changes to the chromosomes actually affect the cells. So we can divide radiation, broadly speaking, into two categories. Ionizing radiation is capable of ionizing atoms, that is, removing electrons from atoms. And these include things like X-rays, neutrons, alpha particles, gamma rays, and beta rays. Non-ionizing radiation doesn't have the ability to remove electrons from atoms, and that includes things like light, microwaves, and magnetic fields, which are then generally less harmful than ionizing radiation, although it's worth pointing out that if they're sufficiently intense, this kind of radiation can actually cause heating, which can of course also damage the body. There are a couple of effects of ionizing radiation on cells. The first is that ionizing radiation can kill cells directly. Right? That is, it can cause cell death or it can prevent cells from dividing. This is called a deterministic health effect. That is, there's a threshold or minimum value of exposure below which this sort of effect will not occur. The second effect is mutations. That is, we talked about changes in chromosomes. Those mutations can be passed on to new cells, and that's what we call a hereditary, it's because it's passed on, or a stochastic effect. And the question here is whether or not there is a threshold dose below which mutations do not occur. And that's pretty much still an open question. If we look at each of these kinds of effects in turn, deterministic health effects, as I said, require some minimum exposure. There are acute effects, things that happen in the short term, over a period of hours to weeks. For a very large exposure, this can be things like radiation sickness, which carries with it a risk of death. At somewhat lower levels of exposure, you can produce radiation burns. And radiation burns are worse in many ways than thermal burns because radiation is relatively penetrating. When you get a radiation burn, it damages a large volume of material, including killing particular cells. It also damages cells in the nearby area, including cells sort of underneath, which is where the healing would usually begin. So because this damage is sort of widespread and even the healing tissue is damaged, radiation burns are much slower to heal than ordinary thermal burns. These are acute effects. They happen over hours to weeks. Later, we can have, over a period of years, we can have other sorts of effects, such as, for instance, cataracts or development of opaqueness of the eye. When we think about stochastic effects, the most important one, the one we worry about the most, is cancer. Right? And so just as sort of a guideline, a 1 sievert dose gives about a 5% additional chance of developing cancer over the period of your life. Now, we should put that in context. This 1 sievert dose is a pretty significant dose. And the overall risk of developing cancer for any reason is about 25%. So even if you get a pretty large dose, you only increase your risk of developing cancer by about 5% compared to a risk that you already had of something like 20 to 25%. The other stochastic effect is the development of genetic mutations. And these are of concern, of course, because they can be passed on to future generations. So what goes along with this idea of stochastic and deterministic health effects are basically two categories of radiation exposure. So acute exposures are high doses of radiation received in a short time. And an example of this would be, for instance, if you should accidentally stick your hand in the main beam of an X-ray diffractometer while the unit is on. This can give you very large doses over localized regions of the body, can cause severe damage in the form of radiation burns, and the damage can be done in seconds. Right? It happens very quickly. It's a little bit insidious, though, because there's no way to detect this radiation exposure. So, for instance, even though an X-ray beam is very intense, when you have your hand in the X-ray beam, you don't feel anything. There's no tingling, there's no sensation of burning. Your body does not have any way of sensing X-ray radiation at all. And so we need to rely on other ways to detect the presence of radiation. The second exposure of radiation, category of radiation exposure is chronic exposure. And this is from continual exposure to low levels of radiation. So for instance, if you work repeatedly with an X-ray unit that has some low-level leak, you might over a period of time be exposed to low levels of radiation many times. And of course, as you receive more and more exposure, the chance of these stochastic effects, things like developing cancer, go up. To put this in context even a little bit more, let's talk about sources of radiation exposure. And there's basically three that we'll think about. First is natural radiation, radiation exposure we get from natural sources. Second is radiation exposure from artificial sources that are just all around us. And everybody in our society is exposed to both of these. And so we refer to these as the background level of radiation. When we think about radiation-producing equipment, now we're talking about occupational radiation exposure, exposure that happens during the course of doing work. Let's look at background radiation first. The artificial sources are here in this blue or teal color. First of all, let's say in context, the total from all sources of background radiation per year in the United States is about 360 millirem, or 3.6 millisieverts. And about 1/6 of that comes from these artificial sources. So these things would be things like medical x-rays, nuclear medicine. So if you are getting treatment for some condition that requires radiation, from consumer products, so things like smoke detectors, and then just sort of general other. It's worth noting that these are averages over the entire U.S. population. So in particular, this nuclear medicine number is an average over the population, but of course, if you are the one person who's actually getting some sort of radiation therapy, your exposure might be much higher. Compared to that, we have all of the natural sources, which are about 300 millirems per year, and the biggest one by far is radon, which comes up from geologic formations underground. On average, contributes about 200 millirems per year to the U.S. population. This depends significantly on where you live. Certain areas in the United States have much higher levels of radon than others. So besides radon, we have cosmic rays, terrestrial radiation from other radioactive materials, elements in the Earth's crust, and then finally our food and our water have some radiation in them. For example, bananas have a high level of potassium. Potassium-40 is radioactive, so when you eat bananas, you're exposing yourself to some level of radiation. If we put it in context with regard to more occupational sorts of exposures and restrictions, as we said, the annual dose in the United States is about 4 millisieverts per year. That goes up depending on your job. So for instance, an airline flight crew gets something like 10 millisieverts per year because they get higher dosages of cosmic radiation, because when you fly high up in the atmosphere, you get less protection from the atmosphere from those cosmic rays. A single CT scan of the abdomen gives you a significant exposure on the order of about 10 millisieverts. In terms of regulations imposed on us by the federal government, by OSHA, radiation workers, and none of us fall into this category. These are people who work in nuclear reactors and similar occupations. The OSHA regulation is to restrict that to 50 millisieverts per year, and then for the general population, which includes all of us, 1 millisievert per year. So that's 1/4 of the annual average dose in terms of just background radiation. If we put this in context of what health risk that talks about, that implies, 10 millisieverts per year means about 300 additional cancer deaths per million people. And as we said, the overall risk is about 25%. Let's provide a little bit more context in terms of relative risk. If you think about things that you do that create a possibility that you will die from doing them, if you can calculate the probability that you'll die, the probabilities for any one thing that you do are actually pretty small. And so we usually talk about these things in terms of what creates a 1 in 1 million chance that you'll die from doing something. And a little bit of gallows humor, the term which is sometimes used for a 1 in 1 million chance of dying is 1 micromort. So all of the things in this list create 1 micromort risk of dying. So smoking about 1 cigarette from the risk due to lung cancer, living in 2 days in New York City from air pollution, driving about 40 miles in your car, you have about a 1 in 1 million chance of dying from an accident. Flying across the country, again, your chance of dying is about 1 in a million. Canoeing 6 miles down a river gives you a 1 in 1 million chance of dying. And then similarly, receiving 10 millirem radiation dose gives you a 1 in 1 million chance of dying from cancer. So at these sorts of radiation levels, which are the levels we're talking about for occupational exposures, or even lower, the risks are really very, very small. So let's talk about exposure guidelines for radiation exposure. And the first is, as with many things that we do when we do experimental science, we try to balance the risk that we are exposing ourselves to with the potential benefit. So we don't expose ourselves to any risk if there's no benefit. So for instance, if there's no potential benefit from doing, say, a particular X-ray diffraction scan, then why do it? Why take any risk at all for no benefit? On the other hand, if there's a significant benefit, then we may be willing to put up with some level of risk. And then the goal, of course, is to try to keep that level of risk as low as possible. So there's a principle called the ALARA concept. ALARA is an acronym for as low as reasonably achievable. We do everything that we can to minimize our exposure to radiation such that we minimize the risk associated with the beneficial activities that we're trying to do in the lab. The exposures that we receive are subject to some dose limit. So at Hopkins, for instance, we monitor the radiation dose that all of our people who work with radiation-producing equipment receive. And then as someone approaches the lifetime dose limit, then we may prevent them from working with radiation-producing equipment anymore. And our goal is always to prevent any sort of deterministic effect, right? We never want to have any radiation burns or any large-scale exposure like that. And we limit stochastic effects by minimizing the exposure of all of our students and workers to radiation from our equipment. So how do we minimize exposure? Well, there's basically three basic principles. The first is time. Right? We try to minimize the time that we spend working with radiation or near radiation producing equipment, and it's relatively obviously less time equals less exposure. So for instance, if you are setting up a diffraction scan in the diffractometer down in the X-ray lab, rather than spending the 2 hours that it takes your scan to run sitting there on the computer surfing the web, you should just leave the room. That way, even if though the chance of you might be exposed to some radiation in that room is small, you basically eliminate that risk if you simply leave the room. So I always recommend that if the X-ray unit is on and you're not doing something on the computer that requires you to be there, such as analyzing other data or something like that, then you might as well leave the room. Lock the door behind you to control access to the room, but leave the room and therefore you lower your risk. We try to maximize distance between ourselves and the radiation producing equipment. And in this context, it's worth to note that about 1.5 meters of air absorbs 90% of radiation produced by typical laboratory equipment, which is what we call copper K alpha radiation. So simply by sitting a meter or two away, you can significantly reduce your exposure to radiation. And finally, we, of course, we incorporate shielding, typically in the form of lead, but can also be in the form of steel. And here we'll note that just 9 microns of lead thickness absorbs 90% of copper K alpha radiation. So shielding can be very, very effective. Let's talk a little bit about X-ray diffractometers specifically, because these are the chief radiation-producing equipment in our department. First thing to note is that X-ray diffractometers do produce very intense radiation, as high as 10 sieverts per second in the main beam. And as we noted earlier, 3 sieverts can cause radiation burns. So even if your hand spends just a fraction of a second in the main beam, that's enough to cause a radiation burn. So that's the first thing to note, is that the X-ray beam, main X-ray beam, produces very intense radiation, and you never want to expose any part of your body to that. Besides the primary beam, other sources of radiation can be scattered beams, diffracted beams, and it's worth to note that these can be very strong. So for instance, the reflections from a silicon single crystal can be up to 90% of the intensity of the main beam. So if you're working particularly on single crystals, you need to know where the scattered beams are, so that you can avoid them. It's possible that there can be tube leaks, so the X-ray tube may not only emit radiation from the window where it's supposed to come out, but it's possible to leak other places. And then it's also worth noting that you can have secondary emission. So for instance, if you shine X-rays on your sample may also fluoresce in the X-ray regime, and those fluorescent X-rays can also be potentially dangerous. The biggest risk, particularly in terms of these deterministic or acute exposures, is accidental exposure of the fingers or hands, particularly to the primary beam. Let's take a look now at a typical X-ray diffractometer. This image is not of a diffractometer from our department. It's actually one that I downloaded from the web, but I like it because the radiation enclosure in this case is simply leaded glass, allowing you to see many of the components of the diffractometer. In this particular case, the diffractometer itself is, as I said, in this leaded glass enclosure. Here is the X-ray tube itself. You can see leads coming into the X-ray tube which provide high voltage, but also water for cooling. The primary or the main X-ray beam would come out of this X-ray tube. It's directed toward the sample holder, which is right here. And then, as I said, scattered rays can come off in any of a variety of directions. So, of course, the region right near the sample where it's possible that you could put your hand in this primary beam, that's the place primarily to be concerned about. As long as we're looking at this image, I'll just point out a couple of the safety features on this particular diffractometer. There are warning lights which come on when the X-rays are on and when the shutter is open. These doors, again, are made of leaded glass, and they have interlocks down at the bottom and up at the top, such that if you were to open the doors while the X-rays were on, either the shutter, which is what allows the X-rays to come out of the tube, either that would close, or depending on the design of this diffractometer, the power to the X-ray tube would shut off entirely. So let's talk about precautions for using X-ray equipment. The first is all modern X-ray equipment is designed in what's called a fail-safe mode. That is, there are interlocks that prevent the X-rays from being on, or again, depending on the design of the equipment, the shutter from being opened if particular criteria are not satisfied. So, for instance, there's shielding that is in place around the X-ray diffractometer. There will be micro switches on the shielding panels, such that if a shielding panel is removed, the micro switch opens. That interlock then prevents the X-rays from turning on or turns off the X-rays if they are already on. The shielding, of course, is there to protect us from radiation sent out in basically any direction from the tube. Similarly with warning lights. There are always warning lights on modern diffractometers that tell you when the X-rays are on and when the shutter is open. These are also designed in a fail-safe way such that if, for instance, a warning light burns out, preventing it from turning on, that also then trips an interlock which prevents the X-rays from turning on, or again will turn the X-rays off. Also, we have automatic shutters. As I mentioned, in particular when the doors to the X-ray diffractometer open, then the shutters close automatically, and again those are a fail-safe design. In terms of the sort of personnel controls that we have, of course we provide training in the form of this video, but also hands-on training with the X-ray diffractometer. There are warning signs which are posted on the door to the lab and also in the lab. We monitor exposure to radiation of all of our users, and when you receive training in the lab, you'll see the film badges which are there, which we'll talk about in a few minutes. This is a way to monitor for leaks from our equipment. If we suddenly see all of our users, or many of our users, receiving some low-level exposure, then we might have an idea that our equipment is leaking radiation. I'll say that in the entire time that I've been at Hopkins, this has never happened. None of our users ever get any exposure, which is above background, but vigilance is worthwhile, and so we always continue to monitor. Finally, we do regular equipment inspections of the radiation-producing equipment, looking for problems with the equipment, how the shutters work, and we also do surveys with radiation meters, Geiger counters, to make sure that the radiation closure is not leaking any radiation. So here's a typical X-ray diffractometer. This is actually the department X-ray diffractometer down in the basement of Maryland Hall. Again, I'll just point out a couple of the main features of this in terms of the safety equipment. Again, you'll notice this big light on top, which you can hardly miss. Right? It will always be on if the X-rays are on. There's also lights on the control panel that tell you when the X-rays are on. There are doors with leaded glass, perhaps leaded plexiglass windows, such that if these doors actually lock when the shutter is open, and if you were to try to open them and successfully open them, then the shutter would automatically close. This is a diffractometer in my lab. Again, you notice warning lights on this little stack over here. There's a light for the X-rays on and a light for when the shutters are open. There's a sign that warns you that radiation could be present. And again, these doors lock when the shutters are open, and if you force the doors open, the shutter will close automatically. So despite all of these controls and the equipment we have in place to prevent accidents, it is potentially possible that someone could be exposed to X-ray radiation in our labs. And it's worth reviewing where those causes of accidents might come from. The first is that someone might decide willfully to violate procedures, or they might violate procedures accidentally due to inadequate training. And so that's one possibility. We try to maintain our equipment in such a way that even if you violate the procedures, you can't hurt yourself. But that might not always be possible. So training is very, very important. What goes along with this, of course, is some level of personal responsibility. That is, even though you are receiving this training and you'll be trained hands-on in the lab on how to use a diffractometer, you have to decide for yourself that you will follow the procedures that you're taught and not violate the procedures. What goes along with that, of course, is that if you don't know a procedure, or perhaps if it's been a while since you received your training and you find that you've forgotten something, you need to ask someone who knows more, the people responsible for the lab, or myself, such that you don't accidentally violate any procedures. Second potential cause of accident is improper equipment configuration. So for instance, if a diffractometer were to lack shielding, or if someone were to defeat the interlocks, those of course could be causes of accidents. If we were to manipulate the equipment while the x-rays are on and the shutter is open, and here and now I'm thinking about things like diffractometer alignment, that of course could lead to a radiation exposure. Again, the equipment is designed in such a way that this is actually not possible, right? That it's not possible to have your hands near the main beam or any other part of your body near the main beam while the x-rays are on and the shutter is open. I will say that sometimes this is necessary. So for instance, in particular cases when we're aligning x-ray diffraction equipment, we need to manipulate certain parts of the equipment while the x-rays are on and the shutter is open. And this of course requires extreme caution, and I will say it should never be done without the permission and probably the presence of the principal investigator responsible for the lab. And in case of the x-ray diffraction equipment in our building in material science, that's me. If anyone was ever trying to align equipment, I would certainly want to know that and probably be there while it was going on, because you have to, of course, be very, very careful when you're doing that. And the final possibility is equipment failure. Even if equipment should fail, again, almost all of the critical pieces of the x-ray diffractometer are fail-safe, in the sense that we have these interlocks that will prevent the x-rays from being on or the shutter from being opened, even if the equipment should fail. So in terms of precautions that we take, the first and perhaps most obvious one is that you should know where the primary, the main x-ray beam is, and where the scattered x-ray beams can go. We never defeat or bypass interlocks, and we don't modify the equipment in any way. We always wear our finger dosimeters. You'll receive a little a small ring that goes on your finger. It should be worn on the index finger of the dominant hand. The purpose of that is to monitor for radiation exposure. The ring badge does not provide any protection in any sense from exposure, but if you should be exposed, it gives us an idea of how much radiation you may have been exposed to. And the reason we wear it on the index finger of our dominant hand is because that's simply the hand that is most likely to be exposed to the primary beam. If you're reaching in to change a sample or something like that, you're probably doing it with your dominant hand. And so that's why we wear the finger dosimeter on our dominant hand. We check safety devices frequently. That's both through the regular inspections, but just also as you use the equipment, you should observe that the various safety devices, the interlocks and the warning lights and the shutter opening and closing are working properly. Going back to the risk of electrical hazards, we don't do any maintenance on the equipment when it's energized, particularly underneath where the high voltage power supply is, or connecting or disconnecting leads to the x-ray tube. We do regular radiation surveys with a radiation meter. When we're using the x-ray diffractometer, we maintain surveillance of the machine so that we ensure that no one accidentally wanders in and could potentially expose themselves, somebody who is untrained. An alternative to this is simply to secure the area by locking the door to the lab. And finally, we keep a logbook of equipment use, including notes about any unusual or unexpected behavior of the equipment, so that we have some idea if things start to go wrong. Despite all of these things, if you think that you may have been exposed to, particularly to the primary beam, the first and most important thing to understand is that there's no need to panic. A significant radiation exposure is a serious event. You do need to get treatment for that, but the damage that's done takes place over hours, not seconds or minutes. So there's no need to rush off to the emergency room or anything like that. So in general, first thing is don't panic. Second thing is you want to get help from somebody nearby. If you really think you've received a significant radiation dose, you're probably not in the best frame of mind to make decisions about what to do next. So tell someone nearby that you think you've been exposed and get their help. You should call the principal investigator, that's me, for the x-ray lab, or the radiation safety officer as soon as possible. If it's after hours, you can go to the hospital, you can go to the Union Memorial Emergency Room, and here is their number. You should probably telephone them first to tell them that you're on your way with a possible radiation exposure. Radiation exposures are not something that they deal with on a regular basis, and so if you call them ahead of time and give them a few minutes to prepare, you'll likely be better off when you actually get there. Finally, if you ever think that you've been exposed, either with a large dose or a small dose, you need to report that immediately as soon as possible to myself. I'm the PI, the principal investigator for the lab, and the radiation safety officer. Actually, practically speaking, if you tell me, I'll report it to the radiation safety officer. So to summarize, it's important to realize that analytical instruments can produce X-rays, and in particular X-ray diffractometers produce X-rays, and they are potentially dangerous. However, with proper training and proper equipment, which we have in this department, the risk of any accidental exposure is very small. As I said earlier, as long as I've been the PI for the X-ray labs in Maryland Hall, no one has ever received any exposure greater than just general background radiation, and we intend to keep it that way. But finally, as I said earlier, there is no substitute for personal responsibility. You have to take it upon yourself to follow the procedures that you're taught, to not willfully violate those procedures or bypass the safety features of the X-ray producing equipment, and to ask if you ever have any questions about how to do things safely or the proper procedures. With that, I'll conclude and thank you for your attention. Again, if you have any questions about radiation safety or safety in general, you can direct those questions to me. Thanks very much.